The question of how the universe began is one of the most profound and fascinating mysteries in human existence. While we don't have a definitive answer, scientists have developed various theories and models based on available evidence and observations. One of the leading explanations is the Big Bang Theory. According to the Big Bang Theory, the universe originated from a singularity, an infinitely small, dense, and hot point approximately 13.8 billion years ago. At this moment, all matter, energy, space, and time were compressed into this singularity. Then, an event known as the Big Bang occurred, triggering the expansion of the universe and the creation of everything we observe today. In the early stages after the Big Bang, the universe was incredibly hot and dense. As it expanded, it also cooled down, allowing subatomic particles like protons, neutrons, and electrons to form. The initial mixture of particles gradually transformed into the first atoms, primarily hydrogen and helium. As the universe continued to expand and cool, pockets of higher density formed. These dense regions eventually became the seeds for the formation of galaxies, stars, and other cosmic structures. Gravity played a crucial role in this process, causing matter to clump together under its influence. Over billions of years, galaxies formed and evolved. Inside these galaxies, stars were born as enormous clouds of gas and dust collapsed under their own gravity. Within the cores of these stars, the process of nuclear fusion occurred, converting hydrogen into helium and releasing vast amounts of energy in the form of light and heat. Stars went through cycles of birth, fusion, and death. Some massive stars ended their lives in spectacular supernova explosions, scattering heavier elements into space. These elements, along with the remnants of earlier stars, then became the building blocks for subsequent generations of stars and planetary systems. Around 4.5 billion years ago, in one such planetary system, the Earth formed. It was through natural processes that life emerged on our planet, leading to the remarkable diversity of species we see today. The evolution of life eventually gave rise to human beings, who developed the capacity to ponder the mysteries of the universe and explore its origins. While the Big Bang Theory provides a framework for understanding the universe's origins, there are still unanswered questions and ongoing areas of research. For instance, scientists are actively studying the nature of dark matter and dark energy, which are believed to make up a significant portion of the universe but remain largely mysterious. Additionally, attempts are being made to reconcile the Big Bang Theory with the principles of quantum mechanics to develop a more comprehensive understanding of the universe's earliest moments. Some physicists propose the concept of cosmic inflation, an extremely rapid expansion immediately after the Big Bang, to explain certain observed phenomena. In summary, the universe began with the Big Bang, an event that marked the birth of space, time, matter, and energy. Over billions of years, the universe evolved, giving rise to galaxies, stars, planets, and life. While many aspects of the universe's origins are still being explored, our current understanding provides a remarkable glimpse into the unfolding of our cosmic history. The Big Bang Theory not only explains the origin of the universe but also provides insights into its subsequent evolution. After the initial expansion, the universe continued to grow and cool, allowing matter to come together under the influence of gravity. The force of gravity caused gas clouds to collapse, forming galaxies, clusters of galaxies, and vast cosmic structures called filaments and superclusters. Within galaxies, stars formed and became the primary sources of light and heat. These stellar objects are responsible for the creation of heavy elements through nuclear fusion. Elements such as carbon, oxygen, nitrogen, and iron were synthesized within the cores of stars and later dispersed into space through processes like stellar winds or supernova explosions. As galaxies and stars evolved, galaxies began to collide and merge, forming larger structures. Over time, supermassive black holes also formed at the centers of galaxies, growing in size through the accretion of surrounding matter. These black holes play a significant role in shaping galactic evolution and the formation of structures known as quasars, which are among the brightest objects in the universe. Around 4.6 billion years ago, our solar system took shape within a vast cloud of gas and dust known as the solar nebula. The gravitational collapse of this nebula formed the Sun at its center, while the remaining material coalesced into a protoplanetary disk. Within this disk, small particles collided and merged to form larger bodies, eventually leading to the formation of planets, including Earth. On Earth, the conditions became conducive to the emergence of life. While the exact origins of life remain uncertain, researchers propose that it could have originated from simple organic molecules in a primordial soup, sparked by lightning or energy from deep-sea vents. Over time, these primitive life forms evolved and diversified through the mechanisms of natural selection, leading to the incredible biodiversity we observe on our planet. In addition to studying the origins of the universe, scientists are also investigating the ultimate fate of the cosmos. Depending on the amount of matter and dark energy in the universe, it could continue expanding indefinitely, or the expansion may slow down and eventually reverse, resulting in a contraction known as the Big Crunch. Alternatively, there is the possibility of a big freeze scenario, where the universe continues to expand, eventually leading to a state of maximum entropy and a lack of available energy. To gain further insights into the universe's beginnings, scientists conduct experiments and observations using advanced technologies. Instruments like the Hubble Space Telescope, the Large Hadron Collider, LHC, and various space probes enable us to explore distant regions of space, study cosmic microwave background radiation, and delve into the fundamental particles and forces that govern the universe. While our understanding of the universe's origin has made significant progress, many exciting discoveries and mysteries remain. Scientists continue to refine existing theories, develop new models, and seek answers to questions about dark matter, dark energy, the nature of space and time, and the possibility of other universes or dimensions beyond our own. In conclusion, the study of the universe's beginning is an ongoing quest that has captivated the minds of scientists, philosophers, and humanity as a whole. Through the Big Bang Theory and subsequent scientific advancements, we have gained remarkable insights into the origins and evolution of our vast cosmos, but the exploration and unraveling of its mysteries are far from over. In recent years, scientists have made significant advancements in our understanding of the early universe and its origins. The study of cosmic microwave background radiation, which is the faint afterglow of the Big Bang, has provided valuable insights into the conditions prevailing during the universe's infancy. Observations of the cosmic microwave background have revealed tiny temperature fluctuations, known as anisotropies, which provide clues about the density variations in the early universe. These fluctuations are believed to be the seeds from which galaxies and other structures eventually formed. Detailed measurements of the cosmic microwave background have been carried out by instruments such as the Planck satellite, allowing scientists to refine their understanding of the universe's early moments. In addition to the cosmic microwave background, the study of high-energy particle physics has also contributed to our understanding of the universe's origin. Experiments conducted at particle accelerators like the LHC have allowed scientists to recreate the extreme conditions that existed shortly after the Big Bang. By colliding particles at high energies, researchers can investigate the fundamental particles and forces that govern the early universe. One area of focus in particle physics is the search for the elusive Higgs boson. Its discovery at the LHC in 2012 was a significant milestone, as it confirmed the existence of the Higgs field, a field that gives particles mass. The presence of the Higgs field in the early universe played a crucial role in the formation of structures, as it allowed particles to acquire mass and interact gravitationally. Another fascinating concept in the study of the universe's beginnings is the idea of inflation. Inflation theory suggests that in the fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching space itself. This rapid expansion helps explain certain observed features of the universe, such as its overall uniformity on large scales and the absence of certain relics from the early universe. While inflation theory provides a compelling explanation for these features, there is ongoing research to further understand the details of the inflationary process and its implications for the larger structure of the universe. Some theories propose the existence of a multiverse, where our universe is just one of many bubble-like regions that emerged during the inflationary phase. Additionally, there are efforts to develop a unified theory that combines quantum mechanics and general relativity to provide a more complete understanding of the universe's beginnings. Currently, the most promising candidate for such a theory is string theory, which posits that the fundamental building blocks of the universe are not point-like particles but tiny vibrating strings of energy. String theory suggests the existence of additional dimensions beyond the three spatial dimensions we are familiar with. The quest to understand the universe's origin is a continuous and collaborative endeavor involving researchers from various scientific disciplines. Through observations, experiments, and theoretical advancements, we are gradually piecing together a more comprehensive and detailed picture of how the cosmos began and evolved over billions of years. While many questions remain, such as the precise nature of dark matter and dark energy or the ultimate fate of the universe, the progress made so far highlights the remarkable achievements of human curiosity and scientific exploration. The study of the universe's origins not only deepens our understanding of the cosmos but also provides insights into our place within it and our connection to the vast tapestry of existence. As scientists continue to explore the origins of the universe, they are also investigating the concept of quantum gravity, which seeks to unify the principles of quantum mechanics and general relativity. Quantum gravity aims to provide a deeper understanding of the fundamental nature of space, time, and matter on the smallest scales. One prominent approach to quantum gravity is loop quantum gravity, which suggests that spacetime is not continuous but rather composed of tiny, indivisible units known as quantum loops. These loops interact with each other, forming a network that gives rise to the fabric of spacetime. Loop quantum gravity provides a new perspective on the nature of the Big Bang itself, suggesting that the universe may have undergone a quantum bounce rather than a singularity. Another area of active research is the study of black holes. These enigmatic objects, formed from the gravitational collapse of massive stars, have a profound impact on our understanding of the universe's origins and evolution. The study of black holes has led to breakthroughs in fields such as general relativity, astrophysics, and even information theory. Recent discoveries, such as the detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, have provided direct evidence of black hole mergers and opened up new avenues for studying the properties of these cosmic giants. By studying the extreme conditions near black holes and their event horizons, scientists hope to gain insights into the behavior of matter and spacetime under the most extreme gravitational forces. Furthermore, the concept of a quantum multiverse has gained traction in certain theoretical frameworks. It suggests that our universe is just one of an infinite number of universes, each with its own set of physical laws and properties. These universes could exist within a vast cosmic landscape, with variations in fundamental constants and initial conditions. The multiverse hypothesis arises from theories like string theory, where different configurations of strings and branes give rise to distinct universes. While the multiverse idea remains highly speculative, it provides a possible explanation for the fine-tuning of physical constants and the anthropic principle, the notion that our universe's properties are finely tuned to allow for the emergence of life. Exploring the multiverse hypothesis raises profound philosophical questions about the nature of existence and our place within the broader cosmic tapestry. In addition to theoretical and observational research, advancements in technology have allowed us to explore the universe in unprecedented ways. Space telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope provide detailed observations of distant galaxies, allowing us to peer back in time and study the early stages of cosmic evolution. Furthermore, the emergence of private space companies and international collaborations has opened up new possibilities for space exploration. Missions to neighboring planets, the Moon, and even future manned missions to Mars offer opportunities to study the geology and composition of celestial bodies, potentially shedding light on the conditions that gave rise to our own planet and the potential for life elsewhere in the universe. In conclusion, the quest to understand the origins of the universe is a multifaceted endeavor, encompassing a wide range of scientific disciplines and theoretical frameworks. Through a combination of observational data, experimental results, and theoretical models, scientists are gradually piecing together a more comprehensive understanding of how the universe began and evolved. While many questions remain, the ongoing pursuit of knowledge about our cosmic origins continues to inspire and push the boundaries of human understanding. One fascinating aspect of studying the origins of the universe is the concept of cosmic evolution. Scientists have developed computer simulations and models to trace the evolution of the universe from its early stages to its current state. These simulations help us understand how the distribution of matter has changed over time and how galaxies, clusters, and superclusters have formed and evolved. Through these simulations, scientists have discovered that the large-scale structure of the universe is characterized by a web-like pattern called the cosmic web. This intricate network of filaments and void stretches across the cosmos, connecting galaxies and galaxy clusters. The formation of this cosmic web is driven by the gravitational pull of dark matter, which constitutes a significant portion of the total matter in the universe. Dark matter, although invisible and mysterious, has a profound influence on the formation of cosmic structures. It provides the gravitational scaffolding upon which galaxies and clusters of galaxies form. Scientists are actively studying the nature of dark matter, trying to detect its presence directly or indirectly and unravel its role in the cosmic evolution. Another intriguing area of research is the study of cosmic microwave background polarization. The polarization patterns imprinted on the cosmic microwave background radiation carry valuable information about the early universe, including the effects of gravitational waves generated during cosmic inflation. By studying these polarization patterns, scientists hope to gain insights into the conditions and mechanisms that drove the rapid expansion of the universe in its earliest moments. Additionally, advancements in observational astronomy have allowed scientists to investigate the distant and ancient universe. Powerful telescopes, such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the upcoming Extremely Large Telescope, ELT, can peer deeper into space and observe galaxies that existed only a few 100 million years after the Big Bang. These observations provide valuable data about the formation and evolution of galaxies in the early universe. Furthermore, the study of high-energy cosmic rays and neutrinos has opened up new avenues for understanding the universe's origins. These particles, which are produced by energetic astrophysical phenomena such as supernovae, gamma-ray bursts, and active galactic nuclei, carry information about the extreme conditions and cosmic processes occurring in the universe. The pursuit of understanding the universe's origins extends beyond the realm of scientific research. It has philosophical and existential implications, inspiring wonder and contemplation about the nature of existence, our place in the cosmos, and the possibility of life beyond Earth. The study of astrobiology, for instance, explores the conditions necessary for life to arise and evolve elsewhere in the universe, offering insights into the potential diversity and prevalence of life forms in cosmic scales. In conclusion, the exploration of the universe's beginnings is a multidimensional endeavor that encompasses theoretical models, computer simulations, cutting-edge observations, and philosophical contemplation. By combining insights from various scientific disciplines, researchers continue to unravel the mysteries of cosmic evolution, the nature of dark matter, the cosmic microwave background, and the conditions that allowed life to emerge in our corner of the universe. Each discovery deepens our understanding of the vast cosmos and our place within it, fueling further exploration and pushing the boundaries of human knowledge. One intriguing aspect of studying the origins of the universe is the concept of cosmic inflation. According to the inflationary theory, the universe experienced an exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion helped to explain several puzzling observations, such as the uniformity of the cosmic microwave background radiation and the flatness of the universe. The inflationary model suggests that quantum fluctuations during this expansion gave rise to the seeds of cosmic structure. These fluctuations eventually led to the formation of galaxies, galaxy clusters, and other large-scale cosmic structures that we observe today. The precise mechanisms that triggered and sustained inflation are still subjects of active research, and scientists continue to refine the inflationary models to match the latest observational data. Moreover, the study of the cosmic microwave background radiation has provided crucial insights into the composition and evolution of the universe. Precise measurements of the temperature and polarization patterns in the cosmic microwave background have allowed scientists to determine the universe's composition, with ordinary matter, and dark energy making up its constituents. One of the most significant breakthroughs in our understanding of the universe's origins came in 2019 with the first direct image of a black hole. The Event Horizon Telescope, EHT, collaboration captured an image of the supermassive black hole at the center of the M87 galaxy. This monumental achievement not only confirmed the existence of black holes but also provided observational evidence for the predictions of general relativity. The image revealed a bright ring-like structure known as the black hole's event horizon, which marks the boundary beyond which nothing can escape its gravitational pull. Studying black holes and their properties not only deepens our understanding of gravity and spacetime but also provides insights into the evolution of galaxies and the formation of cosmic structures. Furthermore, the study of primordial elements and their abundances has shed light on the early stages of the universe. The Big Bang nucleosynthesis theory explains how the lightest elements, such as hydrogen, helium, and lithium, were synthesized in the first few minutes after the Big Bang. Precise measurements of the abundances of these primordial elements in the universe match theoretical predictions, providing further support for the Big Bang theory. Cosmological observations have also revealed the presence of a mysterious force known as dark energy. Dark energy is believed to be responsible for the accelerating expansion of the universe. Its exact nature remains unknown, but it is thought to permeate space and contribute to the overall energy density of the universe. Understanding dark energy is one of the current frontiers of cosmological research, as it poses significant questions about the nature of fundamental forces and the ultimate fate of the universe. In conclusion, the study of the universe's beginnings is a complex and multifaceted field that combines theoretical models, observational data, and technological advancements. From the concept of cosmic inflation to the discovery of black holes and the investigation of dark energy, scientists have made remarkable progress in understanding the origins and evolution of our vast cosmos. Yet, many questions remain unanswered, and researchers continue to push the boundaries of knowledge to unravel the mysteries of the universe's origin and ultimate fate. Recent advancements in cosmology have led to the formulation of new theories and ideas that further our understanding of the universe's origins. One such concept is the theory of cosmic strings. Cosmic strings are hypothetical one-dimensional objects that are thought to have formed during the early moments of the universe. These strings are believed to be incredibly dense and have immense energy. According to some theories, cosmic strings could have profound implications for the structure and evolution of the universe. They could have played a role in the formation of galaxies and other large-scale structures by acting as gravitational seeds, causing matter to accumulate along their length. Detecting cosmic strings directly has proven to be challenging, but scientists are searching for indirect evidence of their existence through observations of their potential gravitational effects. Another intriguing area of research is the study of primordial black holes. Unlike the black holes formed from stellar collapse, primordial black holes are theorized to have originated from the extreme density fluctuations in the early universe. These black holes could have a wide range of masses, from microscopic to supermassive. If primordial black holes exist, they could have several profound implications for our understanding of the universe. They could potentially account for the mysterious dark matter that pervades the cosmos, as well as have implications for the formation of galaxies and the evolution of the universe. Scientists are actively searching for evidence of primordial black holes through various observational techniques, such as gravitational microlensing and cosmic microwave background studies. Furthermore, the concept of a cyclic universe has gained attention in recent years. According to this theory, the universe undergoes a cycle of expansion and contraction, with each cycle representing a new epoch of the universe. The idea suggests that the Big Bang was not a one-time event, but rather a recurring process. In the cyclic model, the universe undergoes periods of expansion, followed by a phase of contraction, culminating in a new Big Bang. This cyclic process could provide an explanation for the observed uniformity of the universe and the absence of certain singularities. Moreover, the study of quantum cosmology and the nature of space and time at the most fundamental level continues to be an active area of research. The quest for a theory of quantum gravity, which combines the principles of quantum mechanics and general relativity, seeks to unravel the nature of space-time and the laws that govern the universe on the smallest scales. The exploration of the universe's beginnings is not limited to theoretical and observational research alone. It is a collaborative effort that involves international collaborations, large-scale experiments, and the development of cutting-edge technologies. From the Large Hadron Collider, LHC, exploring the fundamental particles and forces, to space missions like the James Webb Space Telescope probing the deepest regions of the cosmos, these endeavors push the boundaries of human knowledge and bring us closer to understanding the origins of the universe. In conclusion, the quest to unravel the mysteries of the universe's origins is a journey of constant discovery and exploration. From cosmic strings to primordial black holes and the nature of space and time, scientists are continually pushing the boundaries of knowledge to gain a deeper understanding of how our vast and awe-inspiring universe came into existence. Each new insight brings us closer to unraveling the ultimate cosmic puzzle and provides a glimpse into the profound workings of the cosmos. One intriguing area of research in understanding the origins of the universe is the concept of cosmic inflation. The theory of cosmic inflation suggests that the universe underwent a rapid expansion in the earliest moments following the Big Bang. This inflationary period is believed to have stretched the fabric of spacetime, smoothing out irregularities and setting the stage for the formation of galaxies and large-scale structures. The inflationary model not only explains the uniformity of the cosmic microwave background radiation, but also provides an elegant solution to the horizon problem and the flatness problem. The horizon problem arises from the fact that regions of the universe that are now widely separated were in close proximity during the early stages of the universe. The flatness problem refers to the remarkable flatness of the universe on large scales, which requires a precise balance of initial conditions. While the exact mechanisms that drove inflation are still the subject of ongoing research, the inflationary paradigm has garnered strong support from various observations and experiments. The detection of primordial gravitational waves in the cosmic microwave background radiation would provide direct evidence of inflation and offer valuable insights into the physics of the early universe. Additionally, scientists are exploring the possibility of a pre-Big Bang phase, known as the cosmic singularity. The cosmic singularity refers to the initial singularity where all matter and energy were concentrated in an infinitesimally small point. However, our current understanding of physics breaks down at such extreme conditions, and a more complete theory is needed to accurately describe the singularity. String theory, one of the leading candidates for a theory of everything, suggests that our universe may exist as a three-dimensional brain embedded within a higher dimensional bulk. In this framework, the Big Bang could be seen as a collision of brains or a result of the dynamics of strings in the higher dimensional space. Exploring these ideas requires a deep understanding of quantum gravity and the fundamental nature of space-time. Furthermore, investigations into the nature of dark matter and dark energy continue to shed light on the universe's origins. Dark matter, which is thought to make up a significant portion of the universe's mass, plays a crucial role in the formation of structures like galaxies and galaxy clusters. Understanding its properties and interactions is key to unraveling the mysteries of cosmic evolution. Dark energy, on the other hand, is responsible for the accelerating expansion of the universe. Its origin and nature remain largely unknown, but it is thought to be a property of space itself or arise from a new fundamental force. Research in this area aims to determine the exact nature of dark energy and its influence on the past, present, and future of the universe. In conclusion, the exploration of the universe's origins is a complex and evolving field that encompasses diverse areas of research, ranging from cosmic inflation and the physics of the early universe to the nature of dark matter and dark energy. Scientists continue to develop new theories, refine existing models, and conduct groundbreaking observations and experiments to unravel the mysteries of our cosmic origins. Each step brings us closer to understanding the fundamental nature of the universe and our place within it. One fascinating area of study in understanding the origins of the universe is the concept of multiverses. According to some theories, our universe may be just one of many universes that exist in a vast multiverse. These other universes could have different physical laws, dimensions, and fundamental constants, leading to a diverse array of possible realities. The idea of a multiverse arises from theories like string theory and inflationary cosmology. String theory suggests that there may be multiple compact dimensions beyond the familiar four dimensions of space and time, allowing for the existence of parallel universes. Inflationary cosmology proposes that the rapid expansion of the universe during inflation could have given rise to bubble universes, each with its own set of physical properties. While direct observational evidence for the multiverse is challenging to obtain, scientists are exploring various ways to test this idea indirectly. For instance, studying the cosmic microwave background radiation may reveal patterns or anomalies that could be indicative of interactions between our universe and other universes in the multiverse. Another area of research is the study of quantum cosmology, which seeks to incorporate quantum mechanics into the description of the early universe. Quantum cosmology aims to address fundamental questions about the nature of space, time, and matter at the tiniest scales and earliest moments of the universe. One intriguing concept within quantum cosmology is the possibility of a quantum origin of the universe, where the universe emerges from a quantum fluctuation in a pre-existing state. This idea suggests that the laws of physics may have arisen from deeper quantum principles, and the universe itself may be a result of quantum processes. Furthermore, scientists are exploring the role of symmetry in the origin and evolution of the universe. Symmetry breaking, where a system transitions from a symmetric state to an asymmetric state, is believed to have played a crucial role in the early universe. For example, the breaking of electroweak symmetry in the early universe gave rise to the distinct forces of electromagnetism and the weak nuclear force. Studying the dynamics of symmetry-breaking processes, such as phase transitions, provides insights into the evolution of the universe and the formation of structures like galaxies and stars. Scientists conduct experiments and simulations to understand how different types of symmetries emerge and evolve in the early universe. In conclusion, the exploration of the universe's origins extends to intriguing and speculative areas of research such as multiverses, quantum cosmology, and symmetry breaking. While some of these ideas are still in the realm of theoretical speculation, scientists are actively exploring them to gain a deeper understanding of the fundamental nature of our universe. Through a combination of theoretical investigations, experimental observations, and mathematical models, researchers continue to push the boundaries of knowledge, uncovering new insights into the extraordinary journey that brought the universe into existence. Astrophysicists and cosmologists are also studying the concept of cosmic reionization to understand the early stages of the universe. After the Big Bang, the universe was filled with a hot, dense plasma of charged particles. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, making the universe opaque to light. However, a few 100 million years later, something caused the neutral hydrogen to become ionized again, allowing light to travel freely through space. The process of cosmic reionization is believed to be driven by the formation of the first stars and galaxies. The energetic radiation emitted by these early cosmic structures ionized the surrounding neutral hydrogen, eventually transforming the universe into the transparent state we observe today. Understanding the mechanisms and timing of cosmic reionization is a fascinating area of research that provides insights into the formation and evolution of galaxies and the interplay between matter and radiation in the early universe. Additionally, the study of high-energy astrophysical phenomena such as supernovae, gamma-ray bursts, and quasars provides valuable information about the conditions and processes occurring in the early universe. These energetic events, powered by massive stars or supermassive black holes, release vast amounts of energy across the electromagnetic spectrum and generate intense cosmic rays and neutrinos. By studying these phenomena, scientists can gain insights into the extreme environments and physical processes that shape the early universe. Furthermore, the search for the origin of cosmic inflation and the nature of the inflaton field is an ongoing area of investigation. The inflaton field is hypothesized to be responsible for driving the rapid expansion of the universe during inflation. Scientists are exploring the properties of the inflaton field and its potential connections to other fundamental forces and particles in order to better understand the dynamics of the early universe. In recent years, there has also been an increasing focus on understanding the interplay between quantum mechanics and gravity in the early universe. The study of quantum gravity aims to unify the principles of quantum mechanics and general relativity, which describe the behavior of matter and the force of gravity on different scales. This field of research seeks to provide a more complete understanding of the fundamental laws that govern the universe during its earliest moments. Lastly, the quest to understand the nature of time and whether the concept of a before the Big Bang is meaningful is an intriguing topic of investigation. The conventional understanding is that time began with the Big Bang and there is no meaningful notion of time before it. However, alternative theories and models, such as loop quantum cosmology and the ekpyrotic universe scenario, propose different frameworks where time may have existed prior to the Big Bang. In conclusion, the study of the universe's origins is a dynamic and multifaceted field that encompasses a wide range of topics, from cosmic reionization and high-energy astrophysics to the nature of inflation, quantum gravity, and the concept of time. Through theoretical exploration, observational advancements, and experimental investigations, scientists are continually pushing the boundaries of knowledge to unravel the mysteries of how our vast and intricate universe came into being. Each new discovery deepens our understanding of the cosmic tapestry and brings us closer to comprehending the fundamental principles that shaped our existence. One area of active research in understanding the origins of the universe is the study of cosmic microwave background, CMB, radiation. The CMB is the faint afterglow of the Big Bang that permeates the entire universe. It is a relic from the early stages of the universe when it transitioned from being a hot, dense plasma to a transparent gas. Scientists analyze the properties of the CMB to gather information about the composition, geometry, and evolution of the universe. The temperature fluctuations in the CMB provide insights into the distribution of matter and energy in the early universe. By studying the patterns and statistical properties of these temperature fluctuations, scientists can test various cosmological models and refine our understanding of the universe's origins. Another area of research is the study of cosmic neutrinos. Neutrinos are extremely lightweight particles that interact weakly with matter, making them difficult to detect. However, they are believed to have played a crucial role in the early universe. Understanding the properties of cosmic neutrinos, such as their masses and mixing patterns, can provide valuable information about the conditions in the early universe and the processes that occurred during its formation. Furthermore, the exploration of the nature of dark matter and its role in the universe's beginnings continues to be an active area of investigation. Dark matter is an invisible, elusive substance that does not interact electromagnetically and has only been detected indirectly through its gravitational effects. It is thought to make up a significant portion of the universe's mass and has played a crucial role in the formation of cosmic structures. Scientists are conducting experiments in underground laboratories and utilizing cutting-edge technologies to directly detect dark matter particles or study their interactions with ordinary matter. By understanding the properties of dark matter, researchers hope to gain deeper insights into the fundamental nature of the universe and its earliest stages. Additionally, the exploration of the concept of cosmic seeds and the formation of large-scale structures in the universe is an intriguing area of research. It is believed that small density fluctuations in the early universe, often referred to as cosmic seeds or primordial fluctuations, eventually grew through gravitational interactions to form galaxies, clusters of galaxies, and the vast cosmic web we observe today. Understanding the origin and evolution of these cosmic seeds provides valuable information about the fundamental processes that shape the large-scale structure of the universe. Scientists use sophisticated computer simulations and observations to study the growth of cosmic structures, shedding light on the complex interplay between matter, gravity, and dark matter in the early universe. In conclusion, the exploration of the universe's origins encompasses a diverse array of research topics, including the analysis of cosmic microwave background radiation, the study of cosmic neutrinos, the investigation of dark matter, and the formation of large-scale structures. Through observational studies, theoretical modeling, and technological advancements, scientists are continuously pushing the boundaries of our understanding and piecing together the puzzle of how our vast and intricate universe came into existence. Each new discovery brings us closer to unraveling the profound mysteries of the cosmos and our place within it. One area of ongoing research in understanding the origins of the universe is the study of cosmic inflation. Inflation is a theory that proposes a rapid exponential expansion of space that occurred in the very early moments of the universe. This expansion is believed to have smoothed out irregularities and set the stage for the formation of galaxies and large-scale structures. Scientists are investigating the physics behind inflation and exploring different models to explain its origin and the mechanisms driving it. The discovery of primordial gravitational waves and the cosmic microwave background radiation would provide strong evidence for the inflationary theory and offer insights into the energy scales and fundamental forces operating during the early universe. Furthermore, the study of cosmic nucleosynthesis provides valuable information about the composition and evolution of the universe. During the first few minutes after the Big Bang, the extreme temperatures and densities allowed for the formation of light atomic nuclei such as hydrogen, helium, and lithium. By studying the abundance of these primordial elements, scientists can test and refine models of the early universe. Additionally, scientists are investigating the nature of the cosmic web, the large-scale structure of the universe composed of galaxy clusters, filaments, and vast cosmic voids. Understanding the formation and evolution of the cosmic web provides insights into the processes that shape the distribution of matter in the universe. It also helps in understanding the role of dark matter, which is thought to have played a significant role in the growth of cosmic structures. Moreover, the exploration of quantum gravity and the nature of space and time at the smallest scales is a frontier of research. Quantum gravity seeks to reconcile the principles of quantum mechanics with the theory of general relativity to provide a complete description of the universe. It aims to understand the fundamental nature of space-time and the behavior of matter and energy in extreme conditions such as the early universe and black holes. Scientists are also investigating the possibility of a cyclic model of the universe, where the universe undergoes cycles of expansion and contraction. In this scenario, The current universe would be just one in a series of cosmic cycles, with each cycle giving rise to a new iteration of the universe. This concept raises intriguing questions about the nature of time and the ultimate fate of the cosmos. In conclusion, the exploration of the universe's origins is a multifaceted field that encompasses various areas of research, including cosmic inflation, cosmic nucleosynthesis, the cosmic web, quantum gravity, and the cyclic model of the universe. Through theoretical advancements, observational studies, and experimental tests, scientists are continually expanding our knowledge and uncovering new insights into the remarkable journey that led to the existence of our vast and intricate universe. Each discovery brings us closer to unraveling the profound mysteries of our cosmic origins and the fundamental laws that govern the universe. Scientists are also investigating the possibility of a multiverse, a vast ensemble of universes, each with its own set of physical laws and properties. The idea of a multiverse arises from theories like eternal inflation and string theory. According to these theories, our universe could be just one of many bubble universes that exist within a larger multiverse. Each bubble universe may have different fundamental constants and laws of physics, giving rise to a vast array of possible realities. While direct observational evidence for the multiverse is currently elusive, scientists are exploring various avenues to test its existence. One approach involves studying the cosmic microwave background radiation for patterns or anomalies that could indicate interactions between our universe and other universes in the multiverse. Additionally, experiments conducted at particle colliders, such as the Large Hadron Collider, may provide indirect evidence for the existence of extra dimensions or other signatures of the multiverse. Another fascinating area of research is the study of the early universe using high-energy particle physics. Scientists are exploring the conditions that prevailed in the first few moments after the Big Bang by recreating them in particle accelerators. By colliding particles at extremely high energies, researchers aim to understand the fundamental forces and particles that were present during the universe's infancy. These experiments can provide insights into the nature of matter and the symmetries that govern the early universe. Furthermore, the search for cosmic inflation's physical mechanism and the identification of the inflatant field are ongoing endeavors. The inflatant field is a hypothetical scalar field that is responsible for driving the rapid expansion of the universe during inflation. Scientists are investigating various models and potential candidates for the inflatant field, aiming to understand its properties and the mechanisms that led to inflation. Detecting primordial gravitational waves, which are a direct consequence of inflation, would provide strong evidence for these models. Additionally, the study of primordial black holes offers insights into the early universe. Primordial black holes are hypothesized to have formed from density fluctuations in the early universe, and their existence could provide valuable information about the conditions shortly after the Big Bang. Scientists are devising observational strategies to search for these elusive objects and determine their contribution to dark matter and the evolution of cosmic structures. In conclusion, the exploration of the universe's origins extends to intriguing areas such as the multiverse, high-energy particle physics, inflation, and the study of primordial black holes. Through theoretical investigations, observational studies, and experimental tests, scientists are continually pushing the boundaries of knowledge to unravel the mysteries of how our universe came into existence. Each breakthrough brings us closer to understanding the fundamental nature of the cosmos and our place within it. The study of quantum cosmology is another fascinating area that delves into the origin of the universe. Quantum cosmology seeks to apply the principles of quantum mechanics to the entire universe. It aims to understand the quantum nature of space, time, and matter at the most fundamental level. By considering the universe as a whole quantum system, scientists explore concepts such as wave functions of the universe, quantum fluctuations, and the possibility of a quantum origin for the universe itself. One approach within quantum cosmology is the idea of a quantum singularity, which suggests that the universe emerged from a state of extreme curvature and density but without a classical singularity, as predicted by general relativity. Instead, quantum effects could have prevented the universe from collapsing into an infinitely small point and initiated its expansion. Understanding the quantum dynamics at the very beginning of the universe is a challenging task, but it holds the promise of uncovering new insights into the nature of space, time, and the fundamental laws of physics. Furthermore, the search for a unified theory, often referred to as a theory of everything, is a central goal in understanding the origins of the universe. A theory of everything would unify all the known fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, into a single consistent framework. Scientists have made significant progress in this quest through theories like string theory, loop quantum gravity, and supersymmetry. These theories propose novel mathematical structures and extra dimensions that could provide a deeper understanding of the fundamental fabric of the universe. Moreover, the study of cosmic archaeology involves investigating ancient relics and phenomena in the universe to glean information about its early history. Scientists examine the oldest celestial objects, such as ancient stars and galaxies, to learn about the conditions and processes that prevailed during the universe's infancy. By observing distant galaxies and studying their light, researchers can reconstruct the chemical composition, stellar populations, and cosmic evolution throughout cosmic history. In addition, advancements in observational cosmology, such as the mapping of the cosmic web and the study of cosmic microwave background polarization, provide valuable data for understanding the origins of the universe. Sophisticated telescopes and satellite missions collect detailed measurements of the large-scale distribution of matter, the imprint of primordial density fluctuations, and the polarization patterns of the cosmic microwave background radiation. These observations allow scientists to test cosmological models, constrain the properties of dark matter and dark energy, and gain insights into the early universe's structure and evolution. In conclusion, the exploration of the universe's origins encompasses diverse areas such as quantum cosmology, the search for a theory of everything, cosmic archaeology, and observational cosmology. Scientists are continuously pushing the boundaries of knowledge to unravel the mysteries of how our universe came into existence and understand the fundamental laws that govern it. Through theoretical investigations, experimental observations, and technological advancements, humanity's quest to comprehend the origin and nature of the universe continues to expand our understanding of the cosmos and our place within it. Another area of research in understanding the origins of the universe is the investigation of the nature of dark energy. Dark energy is a mysterious form of energy that is thought to be responsible for the accelerating expansion of the universe. It accounts for the majority of the universe's energy density, yet its origin and composition remain unknown. Scientists are studying various theories and models to understand the nature of dark energy. One possibility is that dark energy is associated with a cosmological constant, which is a fundamental constant of space-time. Another possibility is that dark energy is a dynamic field, often referred to as quintessence, that changes over time. By studying the expansion rate of the universe and the clustering of galaxies on large scales, scientists hope to gain insights into the properties and behavior of dark energy. The ongoing efforts to measure the expansion history of the universe with greater precision, such as through large-scale galaxy surveys and studies of supernovae, aim to unravel the nature of dark energy and its role in the early universe. Additionally, scientists are investigating the concept of cosmic strings and other topological defects that could have formed during phase transitions in the early universe. Cosmic strings are hypothetical one-dimensional objects that are thought to have immense energy density and could have significant effects on the large-scale structure of the universe. The study of cosmic strings and their potential observational signatures is an active area of research that could provide insights into the early universe's dynamics. Moreover, the exploration of the concept of emergent spacetime and holography offers alternative perspectives on the origin of the universe. Some theories suggest that space and time may emerge from more fundamental, non-spatial and non-temporal entities, similar to how properties of a surface can emerge from the behavior of its constituent particles. The holographic principle, inspired by string theory and black hole physics, proposes that the information and degrees of freedom in a region of space can be encoded on its boundary, challenging our traditional notions of space and time. Furthermore, the search for cosmic relics from the early universe, such as primordial black holes, cosmic strings, or relics from the epoch of cosmic inflation, is an ongoing endeavor. These relics could provide direct evidence or indirect clues about the conditions and processes that were prevalent during the universe's early stages. In conclusion, the exploration of the universe's origins encompasses various areas of research, including the nature of dark energy, the study of cosmic strings and topological defects, the concept of emergent spacetime, and the search for cosmic relics. Through theoretical investigations, observational studies, and experimental tests, scientists are continuously striving to unravel the mysteries of how our universe came into existence and to gain deeper insights into the fundamental laws that govern it. Each advancement brings us closer to a more comprehensive understanding of our cosmic origins and the nature of the universe. The concept of quantum gravity is a significant area of research in understanding the origins of the universe. Quantum gravity aims to unite the principles of quantum mechanics and general relativity to describe the behavior of space, time, and matter at the most fundamental level. It seeks to provide a consistent framework that can explain the behavior of the universe at extremely high energies and small scales, such as those present during the Big Bang. Scientists are exploring various approaches to quantum gravity, including string theory, loop quantum gravity, and causal dynamical triangulation. These theories propose different mathematical structures and physical frameworks to describe the fundamental nature of space, time, and the particles that inhabit the universe. Through mathematical calculations, computer simulations, and thought experiments, researchers are attempting to uncover the nature of quantum gravity and its implications for the origin and evolution of the universe. Additionally, the study of primordial gravitational waves offers insights into the early universe. Gravitational waves are ripples in the fabric of spacetime that propagate through the universe, carrying information about the dynamics of cosmic events. Primordial gravitational waves, which originated from the rapid expansion of the universe during inflation, can provide valuable information about the energy scales, symmetry breaking, and quantum effects that occurred in the early universe. Scientists are developing sensitive detectors, such as ground-based interferometers and space-based observatories, to directly detect these faint signals from the early universe. Furthermore, the exploration of the concept of a pre-Big Bang phase, such as the ekpyrotic or cyclic models, provides alternative perspectives on the universe's beginnings. These models propose that our universe arose from a previous contracting phase or collision between branes, hypersurfaces, and higher dimensional space. According to these scenarios, the Big Bang is not the absolute beginning but rather a transition from a previous cosmic epoch. Understanding the dynamics and consequences of these pre-Big Bang phases can shed light on the early universe's nature and potentially explain some observed features, such as the large-scale structure and the distribution of matter. Moreover, the investigation of cosmic anomalies, such as the matter-antimatter asymmetry and the origin of cosmic inflation itself, is an active area of research. Scientists are exploring theories and mechanisms that could explain why the universe is primarily composed of matter, with little antimatter, despite the expectation of equal amounts being produced in the early universe. Additionally, understanding the physical mechanisms that triggered cosmic inflation and the precise conditions required for its occurrence is an ongoing endeavor. In conclusion, the exploration of the universe's origins encompasses diverse areas of research, including quantum gravity, primordial gravitational waves, pre-Big Bang scenarios, and the study of cosmic anomalies. Through theoretical investigations, experimental tests, and observational studies, scientists are continuously striving to deepen our understanding of how our universe came into existence and uncover the fundamental laws that govern its behavior. Each advancement brings us closer to unraveling the mysteries of the early universe and gaining insights into our cosmic origins. One intriguing concept related to the origin of the universe is the idea of a brane world or a higher dimensional universe. According to some theories, our three-dimensional universe could be a brane embedded within a higher dimensional space. These theories, such as the Randall-Sundrum model, propose that the Big Bang was the result of a collision or interaction between branes, giving rise to our observable universe. Exploring the dynamics and properties of brane worlds can provide insights into the fundamental nature of space, time, and the origin of the universe. Furthermore, the study of cosmic microwave background radiation, CMB, has been crucial in understanding the early universe. The CMB is the faint radiation left over from the Big Bang, and it provides a snapshot of the universe when it was just 380,000 years old. Scientists have conducted precise measurements of the CMB using space-based observatories, such as the Planck satellite, to study its temperature fluctuations and polarization patterns. These measurements offer valuable information about the composition of the early universe, the density fluctuations that seeded the formation of structures, and the nature of dark matter and dark energy. Another area of research is the investigation of cosmic inflation beyond the initial expansion phase. While the standard inflationary model successfully explains many observed features of the universe, scientists are exploring modifications and alternative models to address some remaining questions. These include the graceful exit from inflation, the selection of the initial conditions, and the detailed dynamics of the inflationary phase itself. By refining our understanding of inflation, scientists hope to gain a deeper understanding of the earliest moments of the universe's history. Additionally, the study of neutrinos, the ghost-like particles with extremely low mass, provides insights into the early universe and its particle content. Neutrinos were abundant in the early universe and played a significant role in the dynamics of cosmic expansion and the formation of cosmic structures. Scientists are conducting experiments to measure the properties of neutrinos, such as their masses and mixing patterns, which can help constrain cosmological models and provide insights into the conditions shortly after the Big Bang. Moreover, the search for direct evidence of physics beyond the standard model is a vital aspect of understanding the origin of the universe. The standard model of particle physics successfully describes the known particles and their interactions, but it is not a complete theory. Scientists are actively searching for new particles, such as dark matter candidates or particles associated with grand unified theories or supersymmetry, that could provide a deeper understanding of the universe's origins and fundamental laws. In conclusion, the exploration of the universe's origins encompasses various areas of research, including brane worlds, cosmic microwave background radiation, inflationary models, neutrino physics, and the search for physics beyond the standard model. Through theoretical investigations, experimental tests, and observational studies, scientists are continuously pushing the boundaries of knowledge to unravel the mysteries of how our universe came into existence. Each breakthrough brings us closer to a more comprehensive understanding of the cosmic origins and the underlying principles that govern the universe. The study of cosmic structure formation provides valuable insights into the origins of the universe. Scientists investigate how the tiny density fluctuations present in the early universe grew over time to form the vast cosmic structures we observe today, such as galaxies, galaxy clusters, and superclusters. By studying the distribution of matter on large scales and the properties of cosmic structures, researchers can refine our understanding of the early universe's dynamics and the nature of dark matter and dark energy. Moreover, the exploration of the concept of a holographic universe offers intriguing possibilities for understanding the origin and nature of our reality. The holographic principle, inspired by black hole physics and string theory, suggests that all the information and properties of a three-dimensional region of space can be encoded on its boundary, similar to how a two-dimensional hologram encodes a three-dimensional image. This implies that our three-dimensional universe may be a projection or a holographic representation of fundamental laws and properties residing on a two-dimensional boundary. Investigating the holographic principle can shed light on the underlying fundamental structure of the universe and its origin. Additionally, the study of baryogenesis seeks to understand why the universe is predominantly made of matter rather than antimatter. According to the standard model of particle physics, matter and antimatter should have been created in equal amounts during the early universe. However, observations indicate a significant asymmetry in favor of matter. Scientists explore various mechanisms, such as Sakharov's conditions, which involve violations of baryon number symmetry and the behavior of fundamental particles, to explain this matter-antimatter asymmetry. Understanding the processes responsible for baryogenesis can provide insights into the early universe's conditions and the fundamental interactions at play. Furthermore, investigations into the possibility of a cyclic universe or a universe with multiple Big Bangs and Big Crunches are ongoing. Some theories propose that our universe undergoes cycles of expansion and contraction, with each cycle beginning with a new Big Bang. These cyclic models offer alternative explanations for the origin of the universe and the nature of its expansion. Understanding the dynamics and consequences of cyclic universes can shed light on the ultimate fate of our universe and the underlying mechanisms governing its evolution. In conclusion, the exploration of the universe's origins encompasses diverse areas of research, including cosmic structure formation, holographic principles, baryogenesis, and the study of cyclic universes. Through theoretical investigations, experimental tests, and observations, scientists are continuously striving to deepen our understanding of how our universe came into existence and uncover the fundamental laws that govern its behavior. Each advancement brings us closer to unraveling the mysteries of the early universe and gaining insights into our cosmic origins and the nature of reality itself. The study of primordial nucleosynthesis provides insights into the early universe and the formation of light elements. During the first few minutes after the Big Bang, the conditions were such that protons and neutrons combined to form helium and trace amounts of other light elements. By studying the abundance of these light elements in the universe today, scientists can constrain the conditions and fundamental parameters of the early universe, such as the baryon-to-photon ratio. Primordial nucleosynthesis offers a window into the universe's first moments and provides important clues about the nature of the early cosmos. Furthermore, the investigation of cosmic microwave background (CMB) anomalies offers intriguing avenues for understanding the universe's origins. The CMB, which is the afterglow of the Big Bang, exhibits tiny temperature fluctuations across the sky. In addition to these fluctuations, scientists have discovered anomalies, regions of the CMB that deviate from the expected statistical patterns. These anomalies could potentially reveal new insights into the early universe, such as the presence of primordial gravitational waves, cosmic defects, or features in the underlying inflationary process. By studying the CMB at ever-increasing precision, researchers hope to unlock the secrets of these anomalies and gain deeper understanding of the universe's origin. Moreover, the concept of a multiverse has gained attention in recent years as a potential explanation for the origin of our universe. According to some cosmological theories, our universe could be just one of many universes existing within a vast multiverse. Each universe within the multiverse may have different physical laws, constants, or dimensions, allowing for a vast array of possible universes. The study of the multiverse involves exploring the underlying mechanisms and conditions that could give rise to such a diverse cosmic landscape. Additionally, investigations into the nature of cosmic inflation continue to advance our understanding of the universe's early moments. Inflation proposes that the universe underwent an extremely rapid expansion phase shortly after the Big Bang. This expansion stretched the fabric of space, smoothing out density fluctuations and providing a mechanism for the large-scale homogeneity and isotropy observed in the universe today. Scientists are studying the dynamics of inflation, the underlying physics driving this expansion, and its consequences for the formation of structures and the overall shape of the universe. Furthermore, advancements in observational astronomy and cosmology have led to the discovery of exoplanets, planets orbiting stars beyond our solar system. The search for habitable exoplanets and the potential existence of extraterrestrial life raise profound questions about the origin and prevalence of life in the universe. Scientists are investigating the conditions necessary for life to emerge and thrive, studying the potential habitability of exoplanets, and searching for signs of life through techniques such as studying exoplanet atmospheres and detecting biosignatures. In conclusion, the exploration of the universe's origins encompasses diverse areas of research, including primordial nucleosynthesis, cosmic microwave background anomalies, the concept of a multiverse, the nature of cosmic inflation, and the search for habitable exoplanets. Through theoretical investigations, experimental tests, and observational studies, scientists are continuously expanding our understanding of how our universe came into existence and unraveling the fundamental principles that govern its behavior. Each new discovery brings us closer to comprehending the cosmic origins and our place within the vast cosmos. Thanks for watching. Subscribe, like, and share.